Hello everyone, my name is Caio, and in this video I'm going to answer two questions that users sent me about how to connect a manipulator robot with Isaac Sim. In this video I'm going to show you how to use the Sawyer robot in Omniverse and control it using ROS2. So I'm Caio Vitorino, I'm a PhD in electrical engineering. If you want to reach out to me and send questions, emails, please do it. I'll be available to answer you, to meet you, and to help you set up your simulation. Yeah, please feel free to talk to me. And in this video, I'm gonna answer the Abdul question about how to integrate a robot in the simulation like Fanuc, Sawyer, or the Universal Robot. Since I'm going to record a video about how to configure a custom action graph with ROS2 and use it to read and to publish and subscribe to ROS2 nodes using custom messages, for example. In this video, I'm going to do something more simple, like how to use the standard action graphs to connect your robot to the ROS2. Let's begin. And before we begin, please check if you have the correct ROS installations. And if you want to access this documentation, for example, I highly recommend it. Please go to this link, docs.omniversenvidia.com, for example, and go to installation and ROS2, and follow all the steps that are listed here. And in this video, I'm going to use, as I said, the Sawyer robot from Rethink Robotics. Before we begin, please check if your cache settings are okay. For example, the apps should be running, and if they are not, just restart all the services, for example, and just make sure that they are running. And also the Nucleus navigation. If you don't have these apps, you can go to Exchange and install them, the cache, Omniverse cache, and also Nucleus. And here in Nucleus, you have to see the NVIDIA folder, because if you don't see it, you won't be able to use the Sawyer robot, for example. Here from the documentation, it says that you should go to Isaac, Robots, Rethink Robotics, Sawyer Instantiable, but actually the path is a little bit different. It's NVIDIA, Assets, Isaac, the version, Isaac, Robots, Rethink Robotics. And let's open Isaac Sim. In this app selector, if you are using ROS2, just select ROS2 bridge from this option and start the simulation. Okay, Isaac Sim just opened, and I'm going to copy and paste the path to the Sawyer robot USD file. I'm going to paste it in the video description if you want to access the file. Just open the file and make sure that ROS2 extension is running. It's active. If you can't enable this extension, it's because you didn't configure ROS2 properly. Just follow the steps in the ROS and ROS2 installation. So here you have the Sawyer robot. If you hit play, you see that this robot starts moving. It's just because in the drives, you have some target position already configured for this robot. For example, if in this right J1 joint, you have minus 45 degrees. And don't worry, you can use these values, no problem. It won't affect the communication with ROS2. And now we need to create an action graph. But before we begin configuring this robot, just make sure that your you have the articulation root in your kinematic chain. You must have the articulation root in the base of the robot, for example. And for simple implementations that you don't have to consider self collisions, just disable this option. For example, in this case, I'm going to let it disabled. And in the action graph, let's start creating adding the nodes to communicate with ROS2. First, add the playback tick. Now we're going to subscribe to the joint states that we're going to publish from outside. Connect this execution because you need to activate the joint state in every simulation step, for example. You can write a different topic name if you want. I'm going to let just joint command. And then we are going to create the articulation controller to move the robot. In the target print, you need to select the X form that you have the articulation root, as I showed before. And disable this use path and connect all the effort command to the articulation controller, for example. You need to connect the effort, joint names, position command, and velocity command, for example. And also, let's create another node that is going to publish the joint states. Let's connect the execution, and also let's read the simulation time and connect to the timestamp so we can know, so we can have the timestamp data as well of the joint's position and velocity. And also, if you have a different context in your ROS2 environment, for example, you can modify here in the node. I'm going to let it as 0. And let's hit play. And let's open the terminal and let's see if actually we got an error here. It's because we forgot to add the target print. You have to add the X form with the articulation root as well. And let's hit play and let's see if we can subscribe and to the joint state topic. Joint states. Yeah, we can. Here you can see the timestamp, all the joint names that we have here in the physics tribe, for example. Now let's create the ROS2 package to communicate with Isaac Sim. Let's create a folder called Sawyer NVIDIA WS, and let's create the source folder. And here we are going to use a ROS2 command to create the package, some files automatically for us. It's ROS2 package create build type meant CMake because we're going to use C++. The node name is Sawyer node and the package name is Sawyer package. Now let's open VS Code in the workspace directory. And now you have it. VS Code is going to create the .VS Code folder for you like this. And here you can set the opt ROS humble include so you can see the header files and the functions definitions inside ROS. But actually, let's close VS Code and open again. Okay, it seems to work well, but before we begin, let's first add the packages like RCLCPP, the sensor messages as well. And let's link the RCLCPP and sensor messages to our node with amount, target, dependencies, Sawyer node, RCLCPP, and sensor messages. Also, let's add the dependencies here, CPP, and the sensor messages. Now let's import RCLCPP and sensor. VS Code doesn't seem to recognize the library. It's because I don't know, it just disappeared from the C++ properties, but let's add it again. ROS humble include, and let's close VS Code and open again. Okay. Now it seems to work. Let's see. Okay, now it's working. We are going to use joint state because we need to publish the message to Isaac Sim, and here we're going to initialize Isaac Sim with the arguments that we pass to the node, and let's shut down as well, and let's build the package just to see if everything is running accordingly. Okay, it's running. Now let's create a class that's called Sawyer robot. And here we're going to create the class constructor that's called Sawyer robot. Also, we are going to declare some variables. Like before I forget, let's spin. And in this case, let's add the Sawyer robot to the spin, so we can continually publish the messages. Here we're going to create the publisher. That's the type sensor message joint state, and the publisher name is Sawyer pub. Let's also initialize the timer, declare the timer, it's called timer, and we are also going to use a message to publish a sinusoidal trajectory for the robot to follow. Joint state, joint message, and also let's declare some other variables. So we're going to use in the sinusoidal signal, like frequency, time, amplitude, position. I'm going to call it target position and target velocity. And here we're going to initialize the publisher that's called Sawyer pub of the type sensor messages joint state, and that's publishing in the joint command. Now let's declare the timer, initialize the timer, Here we pass the class name, and the callback name is going to call joint callback. And let's create the callback here. It's called joint callback. And let's initialize some variables, like step is going to be 20 milliseconds. Let's use it here. And the frequency is 1. The amplitude is going to be 1 as well. Let's build the package just to see if it's working. And let's source the environment, and let's run the package. Okay, it's running. Now we create the target position. It's going to be sine of 2 times pi times frequency times time, and the position is going to be the target position for each joint. But before we continue, we have to create the message actually. So we're going to create the joint message equals sensor message joint state, and then we create associate the name of the joints. For example, the joint names are the same as you can find in this topic. This topic is being published by Isaac Sim. You can use the same names of the joints. For example, let me write it here. And recreate the message as well for the 8 joints. As well as the velocity. Now we can use the joint message position and associate for each joint message position we have to associate with the target position. Now the time is equal plus equal step divided by 1000 to get it in seconds. Okay, I forgot the same column here. And let's build the package. And then let's run the node. Now let's run plot Yuga just to see what's being actually we are not publishing anything. We have to publish the message, joint message. Let's build the package again. And run the node. So let's see what's being published. Okay, this is the signal that we want. Now let's stop the node and let's do the same for the target velocity. It's the derivative of the position. It's 2 pi frequency times cosine of the same argument. And now let's do the same thing for the velocity, target velocity. And yeah, let's see if it's working or if I forgot anything. And now let's run the node, and we have the velocity associated with the position. Okay, it seems to work well, but the robot may be moving too fast for this signal. So we are going to reduce the frequency to 0.1. And let's build the package again. And let's run the node. And here you can see the new velocity. And yeah, here you can see the robot moving in Isaac Sim. It may be too fast still for the robot to follow this position. You have to make sure that the velocity that's being published to the robot is that does not exceed the maximum velocity of the real robot, for example. So that's it for this video, and thank you for watching this video. If you have any questions, please don't hesitate to send me a message on LinkedIn or by email. I'll be happy to guide you through the setup of your simulation. So thank you, and see you in the next video.